Hi everyone. So in today's session, I'll be taking you through something very ubiquitous. That distribution is normal distribution, and I wanted to derive from scratch as to how do we get the normal distribution, right? The formula for normal distribution and also the mean and variance of that, right? So with that, let's get started. So as we already know, the normal distribution is looks like this, okay? And I'm talking about the mean as 0 because it starts from 0 and it goes something like this, right? So this is the ubiquitous bell curve, all right? And the probability density function for this specific uh, diagram is this, okay? Alright, so I'm going to derive as to how do we get to this function, alright? How do we get this? This seems to be very strange and yeah, a bit intimidating as well. So I'll try to just decode as to how do we get this one, okay? So with that, let's get started. So let's assume this function is something like this, okay? And I'll give you the rationale as to why I'm writing it as like this. So fx, first of all, let us write it as minus x square, okay? Because we see that the maximum happens at 1 at 0, right? So this is 0, the maximum of this function is at 0, and then it tends to taper off in both directions, right? So when we have the exponential as negative 1, so it would mean that it would taper off, right? And the maximum would be at 0, okay? And so this is that function, but the thing is we will also need to have another variable into it. And why is that? Because see, the thing is, this is the probability distribution function, right? And what we would need eventually is minus infinity to infinity fx dx, okay? Because this is probability density function, this should be always be equating to 1, right? But now if I integrate is this particular function, okay, minus infinity to infinity, this won't be equal to 1, all right? So we need to include a few variables such that this specific function, right, becomes 1, such as to satisfy this particular formula, that the integration of fx dx from minus infinity to 1 plus infinity is always 1, right? So let's do this. All right, so let's come back over here. Also, let's derive what is, and I will also give one more clue, the integration of minus infinity to infinity. Let's try to do this, right? What is minus bx square? Let's try to do this. All right, I'm just written that minus bx square because I want to see what is the integration of minus infinity to infinity. For sure, I know that integration of minus e raised to the power minus x square dx, e raised to the power minus x square dx from minus infinity to plus infinity is not equal to 1. So I introduce another variable, and now let us see what exactly is this, okay? So what we'll do is, now this is very critical trick. What we do is bring another I into this, and I'll explain what is the rationale behind this. So let's say e raised to the power minus x squared dx, okay? And because we have included another I, so this time it would be minus infinity to plus infinity e raised to the power minus y square dy. We can't have the same variable, right? Because then it would be minus x raised to the power 4, right? Which sorry, minus 2x square, which doesn't make sense. So we want these two variables to be different, and I'll also explain the reason as to why I'm doing it. If you do this, it becomes e raised to the power minus x square plus y square dx dy. And the beauty of this is x square plus y square, right? So this gives the understanding to us that this is in a form of a circle. X square plus y square is equal to something. That means we can assume it to be a circle, right? The formula corresponds to a circle. And what we do is we replace x equal to r cos theta and y equal to r sin theta, okay? Because this makes the integration a bit easier, okay? So now if you do x square plus y square, okay, this becomes r square, okay? But at the same time, we also need to figure out what is dx into dy, right? Because this comes features into the integration. So for that, we would need the Jacobian, And Jacobian is something very straightforward. It is telling us that okay, if earlier your coordinates was in terms of x, let's say the coordinate was x and y, and if you are then changing it to something like r and theta, okay, so this is our r and this is theta, okay. So if you replace r, changing into a coordinate system of x y to r theta, then what happens to dx and dy, right? What happens to the small displacement in dx and dy? So it is nothing but something like this: dx by dr, dx by d theta, okay, and then dy by dr and dy by d theta. It's essentially talking about once you change the coordinates, right, from x y to r theta, what happens to dx and dy, okay. So let's do this. We had x equal to r cos theta, okay. So dx by dr is nothing but cos theta, all right, and dx by d theta is nothing but minus r sin theta, okay. Similarly, y equal to r sin theta, okay. So dx by dr equal to sin theta, and dx by d theta equal to r cos theta, okay. So now let's put it over here, okay. So I said Jacobian is nothing but dx by dr. So dx by dr is what? Cos theta, and then dx by d theta is nothing but minus r sin theta, okay, and then dy by dr is nothing but sin theta, and then dy by d theta is, sorry, dy by d theta, I should have written it, dy by d theta, okay. Dy by d theta is r cos theta, okay. And this is nothing but a determinant. So once you do this, you will get r cos square theta minus of minus r sin square theta, okay. And this becomes r cos square theta plus r sin square theta, and then this becomes r, okay. So essentially it's saying that, you know, the Jacobian is r, okay. So which would mean that when we are talking about dx dy, all right, so we were over here, we had derived that Jacobian is equal to r, which means, let me write also the symbol for Jacobian, says that it becomes straightforward to understand. It essentially says that it's saying that a small change in x and y, right? A small change in x and y corresponds to what change in dr and d theta, right? So r dr d theta, all right. So this is what we arrive at. So small change in dx and dy, if we change the system to r and theta, it corresponds to r dr d theta, okay. So let's go back. So we had I square as this, okay. This is what we had, no? Yeah, also write minus b. Okay, so let me write minus bx square minus by square, and it becomes minus bx square y square, okay. All right, now when x equal to minus infinity, right, okay, so here is this thing. Let's assume x and y also could, so x and y, right, can vary from 0 to minus infinity to infinity over here, and y also can range from minus infinity to infinity, okay. But if you look into the r end, right, r and theta corresponding, right? If this is theta and this is your r, the maximum value which r can take is infinity, right? The minimum value which it can take is 0, right? Similarly for theta, the maximum value which it can take is 2 pi, which is 360 degree, and the minimum it can take is 0. Okay, so this corresponds to, when you write in terms, it becomes 0 to 2 pi. Okay, that is for theta, and then it becomes 0 to infinity. Okay, for r, right? So we'll, and also, so for that matter, let me write it like this. So I square would become, we'll get into the infinity and plus infinity later. So let's write it like this. So it becomes minus b x square plus y square is nothing but r square. Okay, dx dr was what? Dx dy was r dr d theta. Okay, this is what we got. Let's have the double integrand, and as I said, the d theta, okay, the theta would change from 0 to 2 pi, all right, and the r would change from 0 to infinity, all right. So let's do this. We'll write d theta 0 to 2 pi, okay, and then this guy 0 to infinity e raised to the power minus b r square r dr. Okay, and this d theta 0 to 2 pi would be nothing but theta only. Okay, 2 pi to 0, and then this still remains 0 to infinity. We need to solve this, the r square r dr. Okay, so this becomes 2 pi. Okay, and because pi, and then you replace the value of pi with 2 pi, and then 2 pi minus 0 is always 2 pi, and then this becomes this. Okay, so now what we do? So we do a simple replacement now over here. So let's say br square, let's assume it to be k. Okay, so if br square is equal to k, then let's differentiate it to b r dr. Okay, is equal to dk, correct? And then r dr becomes what? It becomes dk by 2b. Okay, so if we do the replacement, so this becomes 2 pi, 0 to infinity still exists, because when you put r as 0, k becomes 0, and when you put r equal to infinity, it becomes infinity only. E raised to the power minus b r square becomes what? Minus k. Okay, r dr is dk by 2b. Okay, so this 2 and 2 gets cancelled, so we are left with pi by b e raised to the power minus k dk. Okay, and this integral we already know would be e raised to the power k minus 1. Okay, because if we differentiate minus e raised to the power minus k, you will get e raised to the power minus k. That is it. So let's also do this, pi by b e raised to the power minus k, and then because the minus sign is over there, so we will just change this, becomes 0 to infinity, and then it becomes pi by b e raised to the power minus k. Okay, so e raised to the power minus 0 is nothing but 1, right, minus e raised to the power minus k infinity. Now this term e raised to the power minus infinity, which means 1 by e raised to the power infinity, which becomes 0. So we are left with nothing but pi by b. You see, so I square, right, earlier it was, then becomes pi by b, which means I becomes root pi by b. Okay, but then what was I was integration from minus infinity to infinity of e raised to the power minus bx square dx, right? It is coming out to be root pi by b. Now is it equal to 1? It can only be equal to 1 when this condition holds, right? So it would mean that pi by b equal to 1 or pi is equal to b, right? Which need not always be true, right? So therefore, for making this to be equal to 1 in all situations, we would also introduce another variable. So you see, earlier I said was, first of all, let's consider it to be e raised to the power minus x square dx. But then I said when you integrate it from minus infinity to plus infinity, this term won't be equal to 1. So I said, okay, let's introduce another variable and then see that would that be equal to 1. That can become equal to 1, but only under special situation when b equal to pi. So this also doesn't satisfy the condition that always this would be equal to, this term would be equal to 1. So for making that to be always equal to 1, we introduce another variable called a, right? So as we had done the differentiation earlier, so you see e raised to the power minus x square was what? Bx square. Okay, so e raised to the power minus bx square was root pi by b. Okay, so this terms becomes e raised to the power root pi by b. Now this can become equal to 1 because of the interplay between a and b, right? So if you square this, which means a square into pi by b equal to 1, okay, and then which satisfy the condition that a would equal to be root pi by b, right? So if that condition is satisfied, we will have this to be equal to 1, right? And it doesn't depend on a single variable, so we can always say that our original function of normal distribution with the mean 0. And why I am saying with mean 0, because we have considered the simplest form of normal distribution. We are saying that okay, the maximum would be equal to over here at 0, and then over here and here it would be symmetrical, right? So mean is 0, and therefore our integration, the fx becomes equal to a raised to the power e raised to the power minus b x square. Okay, this is our fx of normal distribution, and as I shown earlier, if you integrate it from minus b to infinity, a b x square dx, right, this would become equal to 1. Okay, so this is how we arrive at our normal distribution, that okay, the formula should be a raised to the power minus b x square. But now what is the value of a and b, right? Now that is another thing which we need to find out. So as I have shown earlier, there's one, we have two variables a and b, and we already have a relation saying that a raised to the power okay, wait a minute, just a minute. Okay, so we have got over here. Now our next goal is to derive the value of a and b, and which we have already, this thing we have we have a is equal to root b by b. Okay, b by pi. All right, so let's do one more thing. Okay, so we know the expectation, the mean is 0. Okay, the mean is 0, and there's another thing by through which you can identify that the mean is 0 is because the fx is nothing but e raised to the power, sorry, a into e raised to the power minus bx square. Okay, now if you look into this, this is symmetrical about x and minus x. So if you do f of minus x, okay, a raised to the power minus b into minus x whole square, okay, is equal to a raised to the power minus b x square. So you see f of x is equal to f of minus x, which also means that the mean is centered around 0, okay, by calculus, right? So this is f of x equal to f of minus x, and this is what we have right now. Okay, mean is 0. So let's find out what is the variance. Okay, so we know the variance, and let's say variance is sigma square. We know that the variance is defined as e raised to the power minus x square into e minus e square x. Okay, now we don't know the value of e of x square, so let it be as it is. Okay, but we know that e of x is 0, so 0 square is always 0, so e of x square. Okay, now here comes the fun part. Now what would be e of x square? E of x square, we already know that fx is this e raised to the power minus bx square. Okay, so f of e of x square would be x square into fx. Okay, x square into fx, which means a raised to the power minus bx square dx. Okay, and then we would be integrating it from minus infinity to plus to infinity. Okay, Okay, let's resume. So we have this. So this could also be written as minus infinity to infinity x. Let's write a outside. Okay, x into e raised x into e raised to the power minus bx square dx. Okay, and why I'm writing is because we are going to apply the integration by parts, and which says that integration by part essentially says that once you have uv is equal to uv minus v du. Okay, so what we are saying in this specific formula, let's say x equal to u, and we are saying that, sorry, let's write is u dv. Okay, let's write is u dv, this is u dv. Okay, and then we are saying that dv equal to x raised to the power minus bx square. Okay, dx. If dv is equal to this, then v would be what? V would be integration of x raised to the power minus bx square dx. Okay, and as you see, we can do a simple substitution. We'll say that, okay, let's assume bx square to be y, or let's say another variable called m, or v, whatever. Let's say call it to be m. Then if you assume bx square to be m, then the dm would be 2bx dx, right? So this part x dx would be consumed by that. So that is the beauty of it, right? So I'll explain what I'm trying to say. So let's say v was this, so v was integration of this. So let's say bx square is nothing but, let's call it to be m, as I was saying. Okay, so which would mean that 2bx dx is equal to dm, which would mean x dx is nothing but dm by 2b, correct? So let's write it from here. V equal to ex dx, so x e dx we know dm by 2b, so this becomes e raised to the power minus m, x dx is dm by 2b. Okay, so it becomes 1 by 2b into e raised to the power minus m dm. Okay, and yeah, we are also integrating it from minus infinity to infinity, so let's write it over here. So what we get is 1 by 2b into e raised to the power minus m by minus 1, right? This is what we get. So sorry, while doing the formulation of v, it needs to be a indefinite integral, which means that we don't really need to put the values of minus infinity to infinity, right? Sorry, so sorry for that. So it still is minus 1, and yeah, we can write some constant over here which we don't really care about. So it eventually becomes minus 1 by 2b raised to the power e raised to the power minus m, and then which was minus 1 by 2b, and our m was nothing but bx square. Okay, so minus bx square. So you see the formula of u dv is, when we do integration by parts, is minus uv minus v du, correct? And over here we will definitely apply the integral formula of minus infinity to plus infinity. Okay, so our I, right, we were saying that sigma square, okay, is equal to minus infinity to infinity, okay, x square into fx. So fx was nothing but a raised to the power minus bx square, dx. But then we will need to do one important trick over here, is because this is symmetrical again. You see x square is there minus bx square, so all is x is in terms of x square, so this is symmetrical around x equal to 0. So what we will do is this would becomes 2 of a 0 to infinity. Okay, so this becomes x square into e raised to the power minus bx square dx. Okay, so this is what we have, and then I showed to you that x, when you do the integration of x square into e raised to the power minus bx square dx, right, assuming this x to be u, and yeah, dv equal to x raised to the power minus e bx square dx. So what we got over here, we got was, when you do this, u dv is nothing but uv minus v du. Okay, and this obviously is with the integration of whatever we had. So it was what, 0 to infinity, right? Because we had done this thing. So let's write it back over here. So what we are saying is x square into e raised to the power minus bx square dx 0 to infinity is nothing but x square into e raised to the power minus bx square. Okay, and there would be nothing dx etc over here because we already have done that. Sorry, this would be, yeah, so this won't be, we won't be integrating it, this already is something which would be uv, so we'll just replace it with the actual value. So we'll write 0 and infinity over here. Okay, minus v. Okay, what was v? We found the v to be, where is it? Yeah, this guy. Okay, so 1 by minus 1 by 2b e raised to the power minus bx square. Okay, so minus 1 by 2b e raised to the power minus bx square is our v. Okay, and then what is our du? Du is nothing but dx, correct, because u was equal to x, so this would become dx. All right, so let's solve first part for. Okay, so what it would become? So it would be infinity square minus e raised to the power minus bx square, right, infinity term. But as you would see, so we could also write it as x square into e raised to the power bx square. Okay, now if you look into this, one is polynomial, then other is exponential. The exponential term tends to suppress the behavior of the polynomial, which means that this term would increase rapidly as compared to the term in the denominator, which would mean that this would become quite rapidly infinity as compared to this term. So which would essentially mean something constant by infinity, which would become 0, right? So this term, this specific term tends to 0 as x tends to infinity. Okay, so the first term becomes 0 and then minus, again we are in the same term, 0 into something which would become 0, right? So this term itself becomes 0 and then minus minus becomes plus. So this term would be plus 1 by 2b e raised to the power minus b x square dx. Okay, 0 to infinity. All right, so we have sigma square is equal to, yeah, a of, we had written that 0 to infinity 2 times, right, 2 times x square into e raised to the power minus bx square dx, correct. And then what we found out, what this was nothing but 2a into 1 by 2b into integration of 0 to this minus bx square dx. Now if you look into this, does this ring a bell? E raised to the power minus bx square dx. Yeah, it should, because we had calculated this, you see. E raised to the power minus bx square is something which we had calculated earlier, right? And this came out to be, yeah, so you look into this, we had calculated minus infinity to infinity, right? It was root pi by b. Okay, so it was root pi by b. Okay, so we'll go, yes, as I was saying, we'll go and proceed ahead. We know that, let me write over here, we know that integration of minus infinity to infinity, yeah, e minus bx square into dx is nothing but root pi by b, correct? Yes, this is something which we had derived earlier, which means that, again, if you look into this, this is symmetrical about x equal to 0, right? So we can replace it with as 0 to infinity 2 times e raised to the power minus bx square dx equal to root pi by b, correct? Which would mean that e raised to the power minus bx square dx 0 to infinity is nothing but root pi by b by into 1 by 2. Okay, good one. So let's come over here. We have sigma square. Now I'm coming from here. Okay, let me also increase the space. I think this should be okay. So sigma square was what? Sigma square was 2a into 1 by 2b. So let's write 1 by 2b, 2b, 2 gets cancelled. Good. And then this specific formula 0 to infinity e raised to the minus bx squared dx. So this was nothing but this was root pi by b, root pi by b into 1 by 2. There are so many 2's over here. Okay, good. A by 2b it becomes into root pi by b. Okay. Okay, so which would become a raised to the power 2 a by 2, right, into root and b, b raised to the power 1 by 2 plus b plus 1, right? So it becomes a raised b 3 by 2. Okay, because this was 1 by 2 and then we had 1 at the bottom, so 1 plus 1 by 2 becomes 3 by 2. So we have sigma square equal to a by 2 into root pi into b raised to the power 3 by 2, and at the same time we also had this, you see, we had a as what? A is as to root b by a equal to square root of b by pi. Okay, so what we'll do is come over here, replace a equal to root b by pi, okay, into root b to square root b 3 by 2. So root gets cancelled and we are left with b 1 by 2 and b 3 by 2. Alright. Alright, so let's do this. So what we get is over here b 1 by 2 minus 3 by 2, okay, which would mean b minus 2 by 2 equal to b raised to the power minus 1. Okay, so sigma square becomes 1 by b. Okay, and we had a equal to what? We had a equal to root we had a root b by pi. Okay, so root b by pi, let's write it b by pi. Okay, which would mean that b by pi, right? And we are also saying, so let's square this, a square equal to b by pi. All right, and b is nothing but sigma square. B is nothing but 1 by sigma square. Sorry, my bad. Okay, so b is 1 by sigma square, so 1 by sigma square into pi, and then we have a equal to 1 by root pi into sigma. Okay, so our formula initially we had written was I equal to a raised to the power minus b x square, right? This is what we had written initially, correct? Sorry, there was a mistake. I forgot to write 2 over here. Okay, my bad. So let's write it over here 1 by 2. Okay, over here 1 by 2. Yeah, similarly over here as well 1 by 2 by 2 by 2. Okay, so it becomes sigma square is equal to 1 by 2b. Okay, which means that b is equal to 1 by 2 sigma square, a square is equal to b by sigma, which means that 1 by 2 sigma square, sorry. Okay, so a becomes b by, so we would need to just write as 2 pi. That's what I was wondering. So this becomes 1 by sigma into root 2 pi. Okay, all right, so we had given this, so now let's come back. So I is equal to 1 by sigma root 2 pi into e raised to the power minus b. Now what was b? B was 1 by 2 sigma square, okay? So 1 by 2 sigma square and then x square, okay? So this is the definition, this is the PDF, this is the formula function of any normal distribution, okay, which has a variance of sigma square and which is centered around 0, okay. Oh, one more thing I forgot. So this is something which is centered around 0. Now what if it is not centered around 0? If it is centered around a particular point, let's say mu, okay, so in that case the expectation, the mean would not be 0 but it could be a particular variable called mu, in which case we will need to shift the coordinate system, okay. So this remains as it is, sigma by root 2 pi remains as it is. Instead of x we would have something called as x minus mu, because we have shifted the coordinate system by mu, such that eventually the mean becomes 0. So it by this by 2 sigma square, and this is how we arrive at the PDF of any normal function which has the mean mu and variation as sigma square. And with this we have the mean as mu and variation as variance as sigma square. So this is how we arrive at this beautiful normal function, which we tend to use very frequently, but yeah, in this session I try to take you through that how do we actually arrive at the formula of the normal distribution.